Welcome! Today, we are tackling one of the absolute most vital foundational concepts in computer science and software architecture. We're breaking down the linked list in data structures, specifically looking at how it operates using C programming. Okay, let's dive into this. Picture this. You're building a program, right? And you've assigned a strictly contiguous block of allocated memory for your data. But suddenly, bam, a massive surge of new data comes in. So what happens when your program hits that rigid wall and runs out of fixed memory space? It crashes, it fails, it completely freezes. Traditional static memory simply can't adapt on the fly, and in modern computing, that lack of flexibility is a massive problem. We literally need a way for our memory to expand and connect dynamically, exactly when we need it. So, here's our agenda for this explainer. First, we'll diagnose the static memory problem. Second, we'll zoom in on the anatomy of a node. Third, we'll look at the types of linked lists. Fourth, we'll get our hands dirty performing dynamic operations. And finally, we'll wrap up with real-world apps and the verdict. All right, let's kick things off with Section 1, the static memory problem and the absolute limits of arrays. Notice the stark contrast here. On the left, static representation requires contiguous memory allocation. This is your traditional array. It's got a fixed, predefined size, which basically forces you to guess exactly how much memory you might need before you even run the program. If you guess too low, your program crashes. Guess too high, you're just wasting precious memory. It offers incredibly limited flexibility. Now, let's look at our hero on the right, dynamic representation. Here, memory blocks are created during execution in the heap using functions in C like malloc, which stands for memory allocation. Instead of demanding a huge contiguous block of memory all at once, dynamic representation grabs available bits of memory wherever they happen to be and connects them dynamically. It's flexible, it's efficient, and it is brilliantly adaptive. To really understand how that dynamic connection works, let's move right along to Section 2, Anatomy of a Node, the ultimate building block. Now this right here, this is the golden formula for today's explainer. Node equals data plus pointer. Because our dynamic memory blocks are scattered all over the computer's heap memory in non-contiguous spaces, they desperately need a way to find each other. Think of it exactly like a giant scavenger hunt. Each stop on the hunt is a node, and when you arrive at a node, you find two things. First, your data. That's the actual information or value you were looking for. And second, a pointer, which is the specific clue or address pointing you exactly to where the next piece of data lives. If you're writing this in C, the struct definition is beautifully simple. Inside, we have int data, which holds our integer value, and struct node star next, which is our pointer aiming directly at the next node in the chain. But wait, how do we actually start this whole chain? Well, we use a special pointer called the head pointer. Now, the head pointer doesn't hold any data itself. Its only job is to point to the very first node in our list, so we know exactly where our scavenger hunt begins. Once you have the head, you just follow the pointers from node to node until a pointer aims at null, which simply means the list is finished. Now that we know what a node is, let's look at how we actually arrange them in Section 3, Types of Linked Lists. We'll be looking at singly, doubly, and circular. And this brilliantly illustrates the three main variations we can build. First up, we have the singly linked list. This one's a one-way street. You start at the head, and you can only travel forward until that last pointer hits null. Second, we have the doubly linked list. Now this one gives you bidirectional movement. Why? Because each node doesn't just have a next pointer, it also has a previous pointer, allowing you to walk forward and backward through the entire list. Finally, we have the circular singly linked list. Instead of the last pointer hitting a dead-end null, it literally loops all the way back around and points right at the first node, creating a continuous never-ending circle. You might be wondering, why do we even need bidirectional movement? Well, think of a doubly linked list exactly like hitting the undo or back button on your web browser. Say you visited page A, then page B, then page C. The browser needs a way to instantly travel backward along that exact same chain to get back to page B. By storing those pages as nodes with previous pointers, that backward jump becomes entirely possible. It's a real game changer. So, we've built our lists. Now, let's put them to work in Section 4, Performing Dynamic Operations, where we'll modify the structure. Now, what's really interesting about this slide is how visualizing these operations reveals just how logical they actually are. Let's take a complex operation, like reversing a linked list. Instead of moving all the heavy data around, we simply change the clues on the scavenger hunt. Step 1, we note the original sequence. Step 2, we disconnect the current forward-facing pointers. Step 3, we carefully redirect those pointers backward, step by step, node by node. And finally, step 4, we update our head pointer to look at what used to be the last node, which is now our totally new first node. Boom, we just reversed the entire data structure purely by manipulating pointers. And we can use similar pointer manipulations to dynamically create, display, insert, search, sort, or delete nodes literally anywhere in the chain. But we absolutely must consider efficiency here. Notice the time complexity differences. If you want to insert or delete a node right at the beginning of the list, it is blazingly fast. It has an order of 1, or O of 1, time complexity, because you just update the head pointer and you're done, instantaneous. However, if you want to traverse the list or search for a specific value, well, that has an O of n time complexity. Because the memory is non-contiguous, you can't just skip to the middle like you can with an array. You have to start at the head and check every single node sequentially until you find exactly what you're looking for. So where does all this theoretical computer science live out in the wild? Let's cover exactly that in Section 5, Real-World Apps and Verdict. Believe it or not, this hidden architecture is the absolute backbone of so much everyday software. When you hit next track on a music playlist, that's traversing a linked list. Your browser history? Yup, a doubly linked list. Undo and redo operations in your word processor? Linked lists again. Swiping through an image viewer, managing dynamic memory, plotting graph adjacency lists, handling collisions with hash table chaining, and even building other fundamental data structures like stacks and queues, they literally all rely on the dynamic, flexible power of the linked list to function efficiently. Let's look at the final verdict. The advantages are absolutely massive. You get a completely dynamic size, highly efficient heap memory utilization that doesn't waste unused blocks, and incredibly easy insertion and deletion compared to rigid arrays. But of course, there are disadvantages. You have to sacrifice extra memory just to store all those pointers. You're restricted to slower sequential access when searching, which often leads to performance-hitting cache misses. And yeah, you have to deal with complex pointer management. Let's be honest, trying to keep track of dozens of interconnected pointers dynamically redirecting to each other can sometimes feel like trying to follow a chaotic group text where everyone is talking over one another, and if you lose one pointer, you lose the rest of the entire list. So the crucial point is this. Linked lists teach us how to break free from the constraints of static memory by using pointers to weave a completely dynamic web of data. But consider this. If linked lists unlock dynamic memory and a flat line, could these same exact pointers be the key to building even more complex, multidimensional structures like sprawling graphs and deeply branching data trees? The answer is a resounding yes, and understanding the nodes and pointers we cover today is the foundational first step to mastering all of it. Thanks for exploring this explainer with me today.